Assalamualaikum. My name is Nabil bin Baharudin. We are from Group 2 and we want to present topic Fourier optic for network analysis PBL. Alright. Without wasting time, I will pass to my group member to explain about the integration of Fourier in spectroscopy. Next, I will pass to Lia to explain this.
I'm Akmalia. I will talk of Fourier transform. A Fourier transform is a mathematical transform that decomposes function depending on space or time into function depending on spatial frequency or temporal frequency. An example application would be decomposing the waveform of a musical chord into terms of the intensity of its constituent features. The term Fourier transform refers to both the frequency domain representation and the mathematical operation that associates the frequency domain representation to a function of space or time. The Fourier transform is also of a function is a complex value function representing the complex sinusoids that constitute the original function. For each frequency, the magnitude absolute value of the complex value represents the amplitude of a constituent complex sinusoid with the frequency, and the argument of the complex value represents that complex sinusoid space offset. Can refer for the sine wave graph above. The rate sinusoid can be described by peak amplitude 1, peak to peak, RMS, wavelength. The rate and the sinusoid have a phase differences of theta. Can refer the general formula. I will pass to Anisha.
Thank you, Akmalia. I'm Anisha. I will continue presenting the slides. The top row shows a unit pulse as a function of time, f bracket of t, and its Fourier transform as a function of frequency, f bracket of omega. The bottom row shows a delayed unit pulse as a function of time, conjugate bracket of t, and its Fourier transform as a function of frequency, conjugate bracket of omega. Translation, or in other words, is delay in the time domain, is interpreted as complex phase shift in the frequency domain. The Fourier transform composes a function into eigenfunction for the group of translation. The imaginary part of conjugate bracket of omega is negated because a negative sign exponent has been used in the Fourier transform, which is the default as derived from the Fourier series. But the sign does not matter for a transform that is not going to be reserved. Next slide. The application of Fourier transform in electrical engineering. Among them are Fourier transform spectroscopy is a measurement technique whereby spectra are collected based on measurement of the coherence of radiative source using time domain or space domain measurement of the electromagnetic radiation or other type of radiation. It can be applied to a variety of types of spectroscopy, including optical spectroscopy, infrared spectroscopy, nuclear magnetic resonance (NMR), and mass spectrometry and electron spin resonance spectroscopy. Method for measuring the temporal coherence of the light, including the continuous wave Michelson or Fourier transform spectrometer and the pulse Fourier transform spectrograph. The term Fourier transform spectroscopy reflects that a Fourier transform is required to turn the raw data into the actual spectrum, and in many of the cases in optics involving interferometers, is based on the Wiener-Kitchin theorem. Fourier transform infrared spectroscopy (FTIR) is a technique which is used to obtain an infrared spectrum of absorption or emission of a solid, liquid, or gas. Thank you. Yes.
Okay, thank you, Anisha. Assalamualaikum. My name is Nabil Mahmudin. I will explain about the calculation in electrical engineering. Okay, as you guys can see, this is the calculation for this first step, and this is the skirt. Okay, for the first step, we must 10 ohm over 10 ohm for farad equals to 1j omega c 1 over j omega times 4 1 over j omega 4. V out times domain equals to V out times omega. Okay, next slide. Okay, for the second step, convert the power supply V in times V in times omega. Omega equals to V in times V in times domain equals to V in times omega. Okay, this is the equation, and for the calculation is phi e power of 3 and u equals to pi over 1 and 3 plus j omega, and we will get the answer 5 over 3 plus j omega. Next. Wait, I can't see clearly. Okay, for step 3, apply analysis, find V out times omega. By using voltage divider, V out equals to R2 over R2 plus R1 plus V in. V out times omega 1 over j omega 4 over 1 j omega 4 plus 10 V in times omega. V out times omega over V in times omega equals to 1 j omega 4, 1 over j omega 4 plus 10. And compare H times omega output over input, and we will get the answer 1 over 1 plus j10 omega. And the second page, H times omega equals to output over input. Output H times omega time input 1 over 1 plus j10 omega times 5 over 3 plus j omega. And we will get the answer V out times omega equals to 5 and H j10 omega plus 3 plus j omega. And I will pass the next question to Muhammad Aiman.
Okay, Assalamualaikum. My name is Muhammad Aiman. I will explain four step for the calculation. For the step 4, inverse Fourier transform. Simplify first. V out omega equal to 5 over 1 plus j 10 omega plus 3 plus j omega, and then we need to split first we get 5 over 1 plus j 10 omega plus 5 over 3 plus j omega. We can cancel at the left. We get 0.5, and then at the bottom we get 0.1. We can cancel 10 too. Okay. The next we get 0.5 over 0.1 plus j omega plus 5 over 3 j omega. So we get the answer 2.5 2.5 over 0.1 plus j omega 3 plus j omega. For the next, we out omega 2.5 over 0.1 plus j omega and 3 plus j omega equal to a over 0.1 j plus j omega plus b over 3 j omega and 2.5 equal to a 3 plus j omega plus b 0.1 plus j omega. Let j omega be 0.1, 2.5 a bracket 3 plus 0 negative 0.1 plus b bracket 0.1 plus negative 0.1. So we get the answer 2.5 equal to a bracket 2.9, and then a equal to negative 2.5 over 2.9. So we get the answer for the a equal to negative 0.862. Let j omega be negative 3. 2.5 equal to a 3 plus negative 3 plus b 0.1 plus negative 3. So 2.5 equal to a 0 plus b bracket negative 2.9. So we get the b 0.862. So we out omega a over 0.1 j omega plus b 3 over j b over 3 plus j omega equal to negative 0.862 over 0.1 plus j omega plus 0.862 over 3 plus j omega. Inverse Laplace V out omega to get the V out time domain. V out omega equal to negative 0.862 over 0.1 plus j omega plus 0.862 over 3 plus j omega. By referring Fourier transform table, we get the equation right there. So the answer is V out time domain equal to 0.862 bracket exponent negative 36 x negative minus exponent power of negative 0.61. Okay, that's all from me.
Okay, I'm Elvika Krisi, and I will be presenting about application of infrared spectroscopy. So it is actually to analyze fundamental molecular structure of sample in geological. It used the Fourier transform infrared spectroscopy. It is also used for those following application, which is to analyze the trace amount of water content in normally any hydrous mineral NaM. Also to measure volatile inclusion in glass and mineral. Not only that, to estimate the explosion of potential in volcanic setting, analyze chemotaxonomy of early life on Earth, and also to link biological affinities of both macrofossil and macrofossil. So next slide. Next slide, please. All right. I'll be also talking about the calculation of in infrared spectroscopy. This is the example of how to find impulse response in spectrum, and also to make a graph of the function. So the question above is actually why time domain equal to E negative 4t minus E negative 12t ut, and also E time domain, which is equal to E negative 8t ut. So here we need to find impulse response, which hash omega is equal to output and input, where we can actually clarify that y omega over x omega is actually output over input. So first we have to convert the time domain to frequency domain as shown. So y omega is equal to 1 over j omega 4 minus 1 omega j plus 12, whereas x omega is equal to y over j omega plus 8. So as we all know from the Fourier table, Fourier hash t is equal to hash omega, where 1 over x omega is equal to j omega plus 12. Then hence we can sub in the formula of x and y, and we can solve it to hash omega equal to 1 over j omega plus 3. Therefore, when we compare the time domain and the frequency domain, we can convert it to time domain, which is equal to E negative 2 TUT. So here we have found hash time domain. And then we want to create a graph of spectrum. So by the formula of magnitude, which is equal to square root hash omega times hash conjugate omega. So hash omega, as we can see from the first few steps, it is actually equal to 1 over j omega 3. So modulus hash omega is equal to square root 1 over j omega plus 3 plus multiply 1 over conjugate j omega plus 3. So as we all know, the square root is on above, so we can put the square root below with the power of 2, 1 over square root omega square plus 9. Therefore, that is the graph as shown, where modulus hash omega is equal to 1 over 3, where the graph is a bit of spectrum. Okay, that's all from me. So I'll be passing to my team member to present the next slide. Thank you.
Thank you, Erika. I will continue the slide. So, as you can see here, this is an example for FTIR spectrometer diagram principle. So, consists of two perpendicular mirrors, one of which is a stationary mirror and the other is a movable mirror. The position of the movable mirror is controlled by hand laser. And between these two mirrors, beam splitter at 45 degrees from the initial position of the movable mirror. A parallel beam of radiation from the IR source is passed on to the mirrors through the beam splitter. So the beam splitter divides the beam and transmits half of the incoming radiation to the fixed mirror and the other half to the movable mirror. Upon reflection from the fixed and movable mirror, the light is recombined at the beam splitter. So the recombined radiation is then directed through the sample and focused onto the detector, which is a pyroelectric detector. When the paths are different is 0, all the spectral components are in phase and the output is at maximum. For the next slide, so the conclusion for this Fourier transform infrared spectrometer. So the advantage for the FTIR is a simple and sensitive analytical tool. It provides fast data acquisition tool and simple to operate. And the most useful analytical tool is that the FTIR determine the composition of organic materials. Second, FTIR also is to identify transparent or semi-transparent in organic films. And the third one provides quantitative determination of compounds in mixtures. For the disadvantage for the FTIR, number one, interpretation of the data requires some experience. Number two, no useful detailed database available for the semiconductor processes. And the last one is the carbon dioxide and water sensitive. So I think that's all from us. Thank you, everyone.